Imagine a person who doesn't know much about space observing the night sky through the telescope for the first time. And then he or she stumbles upon this. I'd be surprised if I were them.
Yes, globular clusters are beautiful and interesting objects,
both for amateur astronomers and astrophysicists. For instance, they can tell us a lot about star formation and evolution, as well as about the early universe. But what caught the eye of our unexperienced observer was their spherical shape. At the same time, we already know that many of globular clusters are ancient, not much younger than the universe itself. Some of them are more than 12 billion years old, which means those are quite stable systems. But why do they have such a shape? What holds them together? Why don't they collapse or dissipate? What is going on inside clusters? That's what we're going to talk about today. Globular clusters are groups of hundreds of thousands or even millions of stars bound by gravity, and they have a distinct spherical shape. And all of those stars are in relatively small volume, several tens to a couple of hundreds of light years across. Central regions of globular clusters can contain hundreds of times more stars than we have in our solar neighborhood, and stellar density increases in the center. There are about 160 known globular clusters in our galaxy.
Of course, they exist not only in the Milky Way. They are found in small dwarf galaxies as well as in the larger massive ones.
M87 has about 15,000 globular clusters.
Besides shape, they also got a peculiar location in the galaxy.
In the Milky Way, they are not in the galactic disk, but rather mostly in the halo. And they also could be in the galactic bulge. But as they are very slowly orbiting the galactic center, they can pass through the galactic disk.
Not all of them formed in our galaxy.
Palomar 12 cluster probably had been a part of the Sagittarius dwarf galaxy, a Milky Way satellite galaxy, and later was captured by our galaxy.
As I've said, many of globular clusters are older than 10 billion years. Most of the stars are probably formed from the same giant molecular cloud at about the same time.
Of course, in reality, it's not as simple as that. Stars of multiple generations could be found in globular clusters. Also, there are anomalous stars like blue stragglers, which I already talked about in a separate video.
I might get back to stellar generations in globular clusters in future videos.
Globular clusters consist mostly of old, low-mass red and orange stars. There's almost no interstellar gas, hence no active star formation.
I should mention that there is still no definitive answer to the question how globular clusters form, but there are some models or even groups of models.
According to one set of models, globular clusters began forming in the early universe during or even before reionization. The mass of clusters was determined by the Jeans mass. When regions of higher density in the early universe surpassed Jeans mass, they started to fragment and form stars. Also, dark matter halos could be involved. In other models, clusters formed during early stages of galaxy formation. Gas in young galaxies could condense into clouds of mass comparable with globular clusters. Also, collision of gas clouds could lead to formation of clusters.
Not all of the clusters are that old. They could form recently or even might still be forming.
They can form when galaxies collide, interstellar gas is compressed, and clusters form in the regions of higher density. One such example is Antennae galaxies. This is the Hubble Space Telescope image. These are two interacting galaxies, and we see here many young globular clusters.
The biggest obstacle in creating the one model is uncertainties in initial conditions, but probably in future scientists will get there with new evidence. But let's get back to the shape. Speaking of distinct shapes in the universe, there are two main options. Quite flat disks, for instance, Earth. For instance, our solar system, other planetary systems, and spiral galaxies. Also, there are spheres, planets, stars, globular clusters, and elliptical galaxies.
In both cases, there is symmetry, and systems are in equilibrium at least for some time.
And there's a question. Why in certain cases an object or a system would have an irregular shape, while in others there is symmetry, and why sometimes it's a disk and other times it's a sphere?
Let's look at our solar system. Because of some instability in the region of higher density or some outside influence like a supernova shockwave, a part of a giant molecular cloud starts to collapse under its own gravity. Particles in the cloud are moving in random directions, but the whole cloud had some initial spin, and one direction begins to dominate, and one distinct rotation direction appears. The cloud collapses further, and just like a skater or me who brings arms closer, because of conservation of angular momentum, rotation speed increases, and the cloud becomes even flatter. We can see that effect rotating a ball of clay fast enough, and also on a larger scale. Because our planet rotates, its polar radius is 20 kilometers shorter than equatorial radius. A much more extreme example of this is Haumea, a dwarf planet. It has enough mass to be spherical, but it looks like this because of very fast rotation. So as a result, we get a protoplanetary disk of gas and dust with a star at its center. And planets form in that disk, and later they mostly maintain that orientation. The similar thing happens in galaxies, but on a different scale.
Why don't clusters become a disk?
In the case of the solar system, we have a relatively dense gas where particles collide quite often. As a result, the ones that move in opposite directions slow down after the collision, but the ones that are moving in the same direction accelerate. And because of the initial spin, it wins over and the cloud becomes flat. But in the case of clusters, parts of the cloud collapse into separate stars, and when there is no more gas, even if stars interact, it happens rarely, and they mostly continue to move in their initial paths. To sum up, in the case of a planetary system, the first thing that forms is a disk of gas and dust, and only then planets form in that disk. First structure, then objects. And in the case of clusters, first stars form, and then later a structure of cluster. First objects, and then they settle down in a structure.
But how do they settle down?
When there's so many objects, stellar dynamics is quite complicated. This is not 2 or even 3 bodies. In simple models, stars and clusters were compared to molecules in gas of uniform temperature. Stars are moving in random directions, interacting and not necessarily physically colliding. When 2 stars get closer, they influence each other gravitationally. They exchange energy, and this slowly leads to equilibrium in a system. This takes tens of millions of years, and under gravity, a cluster becomes spherical.
In the case of some elliptical galaxies, there can be another way to this shape.
They can form when 2 spiral galaxies collide. Spirals used to have order, and most stars were moving in the same direction and plane. But collision disrupted orbits of stars, and instead of beautiful spiral structure, we get this. That's what's going to happen to our own galaxy and Andromeda in a few billions of years. We can also make another comparison with a different type of clusters. Open clusters, which are also groups of stars that formed at about the same time, but they can be all kinds of irregular shapes. Well, first, open clusters are much smaller and less massive. They contain way fewer stars. Only hundreds, maybe thousands of stars. Also, they are less massive, and stars are farther away from each other, which means they interact and exchange energy less frequently, and that doesn't lead to equilibrium, which makes globular clusters spherical. Plus, in our galaxy, open clusters are concentrated in the galactic disk, where they are subjected to much stronger external forces, like tidal forces, and their gravity is way weaker to resist that influence.
As a result, they get distorted and deformed, and even completely dissipate, and stars are no longer bound by gravity.
Open clusters could last for hundreds of millions of years, but that's not nearly as stable as globular clusters.
Stability of globular clusters also depends on velocity of stars. If the star is fast enough, it can leave the cluster, but when they're slower, gravity holds them together.
Globular clusters are also subjected to external forces, but their gravity is strong enough to resist. And stars are held together for billions of years, but they still lose some stars that are too fast from time to time. Another question is why so many stars so close to each other don't collapse. On a very basic level, we can compare it to our solar system. Why doesn't the Earth fall into the Sun? Because it's moving. If I set the speed to 0, it immediately crashes into the Sun. Obviously, in the case of globular clusters, it's way more complicated because the number of stars is huge, but anyway, random orbits and motion help to resist gravity.
But still, something is happening. When 2 stars interact, they exchange energy. The star of lower mass speeds up, and the higher mass star slows down.
Because of that, more massive stars migrate to the center of a cluster, and lower mass stars to the outer regions. The process is called mass segregation. A similar thing happens to the blue stragglers that migrate to the center. Actually, there's way more to talk about. Another process that is called core collapse. I haven't mentioned possible intermediate mass black holes in globular clusters and other interesting aspects, so I think I might talk about them in future videos.
Links to all of the source materials are down below in the description, and if you enjoyed the video, leave a like, comment and subscribe. Bye!